the last video, I was doing some SD card testing, and I showed the screen with some of the routines and what they're doing. My next step then is to take that basic SD card functionality and get it working from C code, and then on top of that, get my FAT file system working. So to do that, I'm taking 3 of these routines. There's an init, there's a write sector, and a read sector. And I'm going to expose them from my operating system through a cop instruction. In addition to that, though, I've got some others that I need to add. Other routines that I need to add: get date time on my operating system. And I previously showed the real-time clock through SPI, but I've now exposed that through a cop call so that I can make a cop call and get the full date and time as part of a single call. And then to the right here, you see all the different C routines that I've put together. So there's an SD card init, and really all that does is it calls the cop to do the initialization. Same with the read sector, write sector. Then there's a FAT or FAT16 initialization. I have a routine to list the root directory just to kind of get some initial testing going here. I've got a routine to print contents of a file. I then have a routine to get the system time from the cop call and convert it from BCD into a format that C is expecting, so that when I write to my file system, I can use appropriate dates and times. I have a create file, a delete file, a helper routine that just simply helps me format file names into what FAT is expecting, and then an overall FAT16 test. And that's what I'm going to kind of walk through here as I get into this. And what I'll start with is just simply this screen here, where I have my Tera term in the upper left. That's connected here to my primary board serial output. I have a little command prompt in the lower left I'm going to run a utility on just to basically set up an SD card that I can use, and I'll show you that momentarily. And then my VGA output is being captured in the upper right here. So the first thing I'm going to do, though, is take out this SD card that is in my 265 system and plug it in to my Windows workstation. And you can see currently it's an empty SD card, but basically I'm going to go ahead and close that, and I'm just going to run a little utility here that will format it, and I can give it a label. I'll call it SD card 1. And then when it's done with that, it creates or copies over 3 sample files. These are really simple sample files. So I can see that there's a file 1, file 2, file 3. And if I pull those up, this is what it looks like. File 1 just says text data in file 1. And you'll see that file 2 and file 3 are just as exciting for contents. But some test files that I can put on to this SD card. So I'm going to go ahead and pop that out now and put it into my 265, and I'm going to fire that system up. Now, I mentioned in the last video that I'm hoping to kind of get to a command interpreter type of program. And so what I'm going to do here is actually start working on a shell. And that, if I mentioned command interpreter earlier, probably shell is more appropriate to what I'm building. But what I can do here now is, if I do a help, shell now shows up as one of my options. And I'll go ahead and just clear the screen. And then I'm going to type shell. And in this shell, what I'm doing to start is just a whole bunch of testing with the SD card and then FAT16. And this is all being done from C calling those cop calls. And I will walk through that code at a real quick high level here. But the first thing I do is I attempt to just read the SD card. So I initialize it. If it initializes, I try to read the very first sector, so sector 0 from the SD card. And if that works, I just show the first 16 bytes. And that is what Windows would have formatted it with. And so what you're reading there, this 33, C0, 80, D0, etc., is sector 0, the first 16 bytes basically on the SD card. Then from C, I generate a buffer of test data. I then write that test data to sector hex 20, or in other words, sector 32. And then I read back that. Now, in between, I do, erase out the contents of that memory buffer, just so that when I read it, I know I'm reading real data back and I don't have stale data in memory that I'm accidentally looking at. I read that back. I then, output what it pulled back from the SD card, which should match my pattern of this 0, 1, 2, 3, 4, etc. I then also output, for diagnostic purposes, just some of the different parameter data from the SD card. So where does the partition start on the SD card? So right now this SD card is a 64 gig card. I created a 500-ish megabyte partition. And this is saying that that partition starts at this LBA address of 800 hex. And that gives me some statistics about how many sectors are reserved, what is the FAT size for sectors, the size of sectors for the root, my LBA start for data, and then sectors per cluster, which is 16 sectors per cluster. And then at that point, if that's all worked so far, I just simply say, okay, the FAT16 system is ready to be used. I then do essentially a directory or a listing. And in this case, I do a listing of the SD card, and it comes back with the volume identifier, and I show that SD card 1. I then show that I've got 3 files, file 1, 2, and 3.txt, and then I also show that there's a hidden directory called system ~1. It's something that Windows would have put on there as a hidden folder when I formatted the SD card. Next step I do is I then actually go out to file 1, read the contents and print it to the screen, which you see here. It says text data in file 1.txt. And then I actually create a file, and I create a file called hello.txt. And this is just telling me that it successfully created that file and it has finished the SD card test. So I'm going to turn off my system and take this SD card out, put it back into my Windows system, and just show you what it did. A couple of things. As I look at this, you'll see that those 3 files are still there. Those are the 3 that it listed. But now I have a new file that I created from my C code, which was to create a hello.txt. I can look at the date and time, and that is 3 minutes ago local time on my PC, so it did grab the correct date and time. And I can open this up, and it says, hello from R265 Nibbler. So all of that is working, and what this has allowed me to do is just verify that I can read and write just raw data on the SD card. I can also spin up FAT16, read the root directory, read the files in the root directory, print one of the files out to the screen, and then I can also create a file. Now, something else I can do, I'll go ahead and put this SD card back in, and I'm just going to run the same thing again here when it comes up. But one of the things that I also did is that if a file exists, it then turns around and will go ahead and erase the file first. So I also have support to delete a file. You might give my VGA capture a second to sync here. Okay, so up this comes, and now I'm going to run just basically the same thing. I'm just going to say, oops, run my shell again, and goes through the same thing. But this time it says, towards the bottom, you'll notice it says an existing file was found, and it deletes it. And so now I should be able to turn my system off. Now on my Windows PC, this is probably going to look identical, except for maybe a new file date and time. And now it says 305, but basically it had detected there was already a hello.txt. It erased the hello.txt, created a new hello.txt, and that's what you're seeing here. And again, you're seeing the date and times all come through just fine. Now, I guess on the serial over here, I am, writing out when I make any cop call that does something with an SD card command. So command 0, 8, and then the 5541 pairs, I do some of those. Anytime I make a call to set the address for where on the SD card I'm going to be working, I log it out on my serial. So I know right away I was trying to read the very first sector, and then as I see I was trying to read sector 20 hex. I did a couple of reads there. One would have probably been to read it, and one would have been to write it, actually the write and then the read. And then this down here is after I reinitialize the card, which wasn't necessary, but my routine does a reinit of the card. And then as I went through and I read the FAT file system, I looked through all the files in the root. I found a file, I printed the file up to the screen, I created a file. These were all the calls that were being made to these addresses on the card to actually query all of that. So there's a lot going on to make that work. And real briefly, if I just pull up the code and walk through this for those of you that are kind of following through this and want to look at the code, I have these main folders, if I can get this collapsed correctly. So I've got my VS Code folder, I've got my secondary AV board code, the primary, the common, and the source. Source is any of my C coding. But in the common, I'll just point out, I did add some additional cop calls. So the last time I would have been in here would have been with some of this drawing type of work a few videos back. But I've now added in SD card read sector, SD card write sector, SD card init, and a get date time. So those are 4 new cop calls that I've added to my operating system. And on the operating system, essentially, then I can come in here and see that I have those routines, so that when a cop instruction is raised, that interrupt is handled. These are the interrupt handlers or routines that are being processed in the interrupt handler. So again, I've got a call out to my read sector, the write sector, and those take in parameter data for the LBA. So when I make a cop call, I first jot down into some memory that both my OS and the C application have access to of where is the LBA. And then I go ahead and say read sector. It reads which LBA I want to work with. It sets it, and then it reads out that sector. And it reads it out to some memory that both the operating system and C have access to. Write sector is the exact same thing. Basically, I say, where is it that I want to write? I then write it out. There's also an init, and then there's a get date and time. And the get date and time, when it's done, it does store all of the data into a space on memory called syscall parameters. And that syscall parameters is a certain spot in memory that my C also has access to. And also, as I write these routines, there is a status byte that I'm writing back so that the C caller knows what was the outcome of this cop call. Did it succeed? Did it fail? That's what these are doing down here. These are going to go ahead and store something back into a status location. And that is the actual status of these, like write sector. So if it fails, which they will, then can fail, my C application knows that it failed and can respond accordingly. So that's my cop functionality kind of up here in my operating system. So then from my C code, I have this here, and I probably should have collapsed all this like I've mentioned in previous videos before I opened it. But let me just get a bunch of this collapsed, and we'll look at it at a high level. Okay, looks like I got all that. Maybe one thing I will point out before I get into the C code, there is within my C project a rules file. I did come in here and I ended up making the stack size bigger. So my stack was basically 4K. I bumped it up to 6K. And so that was a combination of setting up this rules file accordingly. And when I actually go out and do the compile, I've added in a parameter that says stack size, and I specify the stack size. And that way I get a little bit more room in the stack size. And in the rules here, I can kind of see what addresses I'm giving my C application. But basically this 4,000 to 6,000 for application RAM data. So the 4,000 range, 5,000 range. And then I give the entire 6 to stack memory. And I was thinking here, I do specify this. I probably need to come up here. I notice this isn't quite large enough. This should be I'm going to increase this just a little bit. I'm going to go to 7, 7. So that should match. So I'm going from 6 to 77FF. And I'll have to double check that that works, but I think we should be good there. So I'm getting a little bit more memory than what it had before. It defaults to 4K, and I bumped it up now here to 6K if I've got all that right. But back to my C, I put in this, I've got my main, of course, and main is just calling a FAT16 test. FAT16 test then is doing things like output to the screen and say I'm initializing the SD card, and then I go ahead and I do an init. And I can jump up to the init and see that all I'm doing is a cop call. So cop13 is my initialization, and then it jumps to my OS essentially, and it does all of the initialization. So the C program, now anytime it wants to init the SD card, it just says SD card init, and it's that simple. After I initialize, if that did succeed, so the result is 0, I then say, yep, it initialized, otherwise I'll throw an error. Then I'll do a read test. And here I'm going to just let the user know I'm reading from sector 0 on the SD card. And then I have a routine that is SD card read sector, and I pass it a 0. And that read sector then is doing a cop call 11. And it's first placing into my, I have a spot in memory that is meant for parameters. It's a parameter block between any of my C apps and the OS. And I'm just going to go ahead and store there the block number that I am asking for. So this is going to go ahead and grab the contents of that, and then essentially I can now read through the contents that got stored. And so it goes in, it does that, it stores the results into a location SD card RAM buffer, which I just put this up here that points to that spot that basically I'm setting aside half a K as a buffer. So 512 bytes as a buffer anytime I do any I/O with the SD card. Probably more efficient would be to have a lot more buffers or a larger buffer there, but that's all I'm doing for now. It's just 512 bytes for everything that I'm doing. I gave it a friendly name so that I can come down here and now say, just run through it and print it out, or print out at least the first 16 bytes of it here to the screen. And that was on my output when it showed that. So that was if it succeeded. If it failed, it gives me a message that it failed. Then I do a write test, and basically same thing. First of all, I fill the buffer in RAM with some data that's just counting from 0 on up. Then I go ahead and call the SD card write sector and tell it I want to write to sector hex 20. And as you can guess, this is going to be a simple, just a simple cop call. So I again put the block number into this parameter block in RAM. I make the cop call, and then everything else is happening on my operating system side of things. So then I continue down through this. I got done with that, and I say, yep, that write command was accepted. I then clear the buffer in RAM, and then I read back that same information back from RAM. So, from RAM. So I clear out the RAM. And then I read back from the SD card into that RAM again. So I wrote it, now I read it back. And then I just validate. And I don't even really validate here. I just simply output it to the screen, the first 16 bytes. And again, if I see my pattern there, I have pretty good confidence that just the raw SD card writing and reading is working from my C code. And then I get through the end of that. But then after that, I want to start using FAT, so the FAT16 file system. So I have an initialize FAT routine. Oops, let me go back to that. So this FAT16 init is this routine, and there's quite a bit here, so I'm not going to go through all of this. But the first thing it does is just make sure the SD card is initialized, and then it's got to look at things like master boot record. It has to look at a BIOS. There's a BIOS block. BIOS parameter block, maybe is what that is, so short for BPB. But basically getting information about the SD card. And then I store into these global variables all of this information. And that's some of what I print out on the debug output on the test as I run it on my system. And maybe I'll just, so we have that up, I will pop this SD card back in and just get that screen pulled back up. So that basically gets my FAT initialized, and at the end of it, I do have a debug print, and that is what prints out this block on my screen that says, you know, here's where these things came in value-wise. And if I go back, I do have it booted back up. And I will go ahead and do my shell command again. But if you look at this right here, this is what it's printing out. It's printing out these values. So I know what did it pull back from, you know, the MBR and that BIOS parameter block. So then once I'm done with the debug print of that, I've done my initialization. And if I step back one more, and then after that, you know, I just say, okay, the FAT system's ready. And then I have a routine that lists what's in the root directory. And if I go to the routine for that, you know, it looks like this. There's a fair amount to it. But basically, it's going to iterate through, you know, all of the listings. It's going to have to go ahead and read a sector from the SD card, basically saying, go to this location. This is where I need you to read. And it's going to try to read that and then grab the directory entries from that and then basically print those out to the screen. I'll update this to also show, you know, date and time stamps, things like that on the files, basically some of that metadata. But this is just a routine that currently looks at that root directory. Now, this is limited in the version that I'm using right now that I wrote. It's not... If I had a really large root directory, lots of files, this is not going to be able to handle it quite yet. So I know I have more work to do, but this is enough to get me going. So if any of you are looking at the code, keep that in mind. This is kind of a start of an implementation, and I know there's more work to be done to make it support, you know, the full 500 meg partition that I'm looking at. I then have this routine that does print contents of a file, and basically that then goes out and make sure that, again, things are initialized. I have to then go find a specific file, and the file that I'm having it find is this file1.txt. So I've got a helper routine that you give it a what we would normally use, you know, file1.txt, but it's got to format it. It's got to make it be exactly the 8 and the 3, so 11 characters. Without a dot, and it's got some formality in that structure on where if you only had like 4 characters, or in my case, if I say test 1, 5 characters, the other 3 have to be padded with spaces. So it has to be this 11 characters. This little routine does that work for me, which if I come up here, you know, it looks something like this. And then also making sure it's in all caps. That's another part of this. So fill it in with spaces. Make sure it's the exact format I'm looking for, and make sure it's in all caps as it does that. So then this basically goes through and will look for the file, and then it's looking for files with certain attributes, but basically this is saying print that file. You know, so you got to go find the file, you got to read the data for the file, and then actually take that content. And if you find the right file, read and print in this case, the first cluster of that file. And so that's what this does. So it's really only reading the first 512 bytes. Again, for what I'm doing for now, this is enough of a test. But later I would have to say, well, if it's a file that contains multiple sectors, is probably a better way to say it than clusters, but then go ahead and run out through all those sectors to print that out. You know, so you have how many sectors per cluster. It could be multiple clusters, but this has got some logic then to at least get the beginning of it printed out for me. Then after I print out a file using this print file contents, then I try to create a file. And so I create a file called hello.txt. I give it you know, this content that says hello from R265 Nibbler. And if it succeeds, it says one thing. If it fails, it says something else. And that create file is up here. And again, you can all look through this and kind of take your time to go through it. And I've got a lot to improve here. And there's stuff that I'm still kind of learning my way through, or a lot of stuff I'm still learning my way through as far as FAT is concerned. So I'm sure there's a lot of mistakes, and I recognize that already, and I'll have more cleanup to do. But this comes in, if I say to create a file, the first thing it tries to do is delete it. It just blindly says, if you're trying to create this file, just delete anything that matches it to start. Now, in the future, of course, I'll probably prompt the user and say, this file exists. Do you want to proceed? Yes or no? But all of that user input I need to get put into my shell to deal with running a command and then prompting the user, getting input, recognizing the enter key, and then being able to work through the code branching based on what the user's selecting. But this deletes the file. Then it goes through and says, well, I need to go find a blank spot on the SD card. So it's got to find a spot to do that. And this is code that goes through. It tries to find a free space. Once it finds a free space, then it basically is going to zero out some of that. It's going to write in a file name and extension. And of course, it's going to get all of this written back, to the file system. So it's actually got to write the file. It's got to update the FAT table, etc. And here's where I'm including the timestamps. So the appropriate timestamp stuff is being written to the appropriate offsets of where this entry is being stored. So I'm storing a creation date, last access, last modified, start cluster, and file size. And then I write all of that back to the root directory. So there's a lot there. And, what I have so far appears to be working consistently well. And then that gets me to the end of this test. And then the test gets out here and says finished with the SD card. And what you see over here then is showing that. So again, you can see the output as this went. I did a raw sector read up here. Then later I wrote something out to a different location in a raw way, and then I read it back. That all worked. I then also listed out some of this these raw parameters that I was retrieving from the SD card. I did a directory. I showed the output of a file. I then said, go ahead and create a file called hello.txt. As part of that, if it exists, it deletes it. So I at least notify the user that, hey, this file was found, I'm deleting it. Then it recreates it, and then it finishes up the SD card test. So that is all going. And if I run this one more time at this point and I say, well, go ahead and run that shell another time, my vertical scrolling is working, which is nice. Not real high performance, but it works. But as it's scrolling up, you can see that it's continuing to work through all this. It again found the file, it deleted it, etc. So I think I've got the basics, and I do mean basics, as with all of this, of the FAT system running, and I'll have a lot more to do. But so from my C, I'm using FAT. The FAT is leveraging cop calls over to my OS. My OS is then jumping from those cop calls out to the functionality for the SD card that I was walking through in the last video. And that's all performing well. I'm doing some debug output out to my serial as part of this, but I'll work on performance. Right now I'm really focused on just getting it to work. And it seems like I'm making progress there. And then in time, I'll have to come back and do cleanup. I know there's a ton of stuff on the C side that I can be doing. I think the next thing I really need to work on is just user input through this shell. So allowing the user to run commands like do a directory, do a deletion of a file, rename a file, all of those types of things. But that's going to require that the user can type things in with parameters, multiple parameters that I have to be able to parse, maybe prompt the user for things, take user input as part of that prompt, etc. So I think I need to get some stuff done with that, and I'll be working on that. That's what I have here. So again, in the last couple of videos, I've gotten the SPI working, gotten the SD card working, and now have the file system working, and a start of a shell from C that is accessing basically my operating system and hardware through cop calls.